All right, so this video is going to go over the dynamics and Newton's law review. So let's get started. So it says number one, define a force. So that is a push or a pull on an object. Okay, so you don't have to get too technical on that. That's just basically what a force is. So who proposed the first concept of inertia? So remember, inertia was, when we talked about that, it was mass, which we'll talk about that more in this next question. Okay, but Galileo was the first one who actually kind of proposed that concept. And then Newton just kind of refined it. Okay, so number three, state Newton's first law, the law of inertia. Okay, so it basically says an object will stay at rest or in constant velocity unless an unbalanced force acts on it. Okay, so that has to deal with mass. Okay, so inertia basically is mass. Okay, so think about is if you have like a heavy object sitting on the ground, like a big 500-pound ball, okay, that is going to basically, it's going to be hard to get it up off the ground. It wants to stay at rest. Now, if you were to take that 500-pound ball and start rolling it down a hill, okay, it's going to be very hard to stop it because it's going to want to stay in motion. Okay, so basically the law of inertia means mass. The more you have of it, the more it wants to stay at rest or the more it wants to stay in that constant motion. In order to change that, you'll need an unbalanced force in order to do that. Number four, under what conditions will equilibrium or balanced forces exist? That is when your net force equals out to zero. Okay, so that'd be 0 newtons. That means all your balances are balanced out. Now, in order to achieve that, you could be either at rest or you could be moving at a constant velocity, but either way, your acceleration has to be 0. Okay, because remember, F net equals mass times acceleration. If you're not accelerating, then therefore you have no net force. You can still have forces acting on the object, okay, but that basically means that they all balance out and cancel each other out. Number five, list the 4 fundamental forces. Okay, so we don't need to get too in deep on this. Okay, so the strongest would be your strong nuclear. Okay, not too hard to remember that one. It literally says strong in the word. Okay, your second one, your next weakest would be electromagnetic. And you do not need to really know what each one is. Okay, I would just know the strength. Okay, and then you have a weak nuclear. And then actually your weakest one would be gravitational. Okay, which of the following would have more inertia, you, your car, or your house? Well, that's going to be the house because remember we said that mass equals inertia. The more mass you have, the more inertia you have. Draw a free body diagram of a truck moving at a constant speed on a level surface. So I'm going to draw my level surface. Here's my truck. Okay, we're going to say it's going to the right. We have an applied force. Okay, so that's someone's pressing the gas. Now, if you're going at a constant speed, that means your frictional force is going to be equal. Okay, so those both have to be the same. Now you also have the force of gravity pulling it down, and then you have what's called the normal force is pushing back. Okay, so that road is pushing back the same amount that the gravitational force is pulling down. Now, if you wanted to show something that was either slowing down or accelerating, if this truck was accelerating, your FA arrow would have to be bigger. Okay, so that means your FA would be bigger than your FF. If you wanted to show that it was slowing down, your FF would have to be bigger than your FA. Okay, so that's how you show that unbalanced force. Okay, so let's move on to the next question. Okay, number 8, state Newton's second law, the law of acceleration in words. Okay, so that basically says that acceleration is directly proportional to force. So that's one aspect. So that means if one goes up, the other one goes up. If one goes down, the other one goes down. Okay, but it also says that acceleration is indirectly proportional to mass. Okay, so that means the bigger the mass you have, that means the harder it is to get you up to speed. Okay, it's harder to accelerate if you have large mass. Okay, think about like a motorcycle versus like a semi-truck. Okay, so the motorcycle has very low mass. Okay, so it can accelerate quickly versus a semi-truck can be thousands and thousands of pounds. So it's going to take quite a while for that thing to accelerate. Then it says state Newton's second law, the law of acceleration in formula form. So what we've been doing is F net equals ma. Okay, number 10, a force of 4 newtons accelerates a 5 kilogram mass from rest. What is the acceleration? So I have a force, I have a mass. It says from rest, so that means VI would be 0. What is the acceleration? You're looking for A. Now, I was given VI here as 0, but I may not even have to use it. If I'm just looking for acceleration and I have force and mass, all I have to do is F net equals MA. So 4 equals my mass, which is 5, times A. So divide both sides by 5. And you get an acceleration of 0.8 meters per second squared. Number 11, a 10 kilogram mass is acted upon by a 20 Newton force. So we have our mass, we have a force. How long will it take? So you're looking for time to accelerate the body from 6 meters per second to 8 meters per second. So there's VI, there's VF. So we're looking for time. Well, the only thing that has time is our Daffy T. Okay, so we're going to set it up. So VI would be 6. VF would be 8. We're looking for time. Okay, I don't have A and I don't have distance, so I don't have enough there. But I do have enough to do F equals MA. So I'm going to do 20 equals 10 times acceleration. So divide both sides by 10. The acceleration of 2 meters per second squared. So now I can plug that in on my Daffy T. I put that 2 over there. And that means I don't care about distance. So make sure you use equation number 1. So you're going to do VF equals VI plus AT. So 8 equals 6 plus A, which is 2, times T. Okay, do your math. Subtract 6 from both sides, divide by 2, and you get a time of 1 second. Number 12, a wooden block traveling at 5 meters per second west. Okay, so we have a velocity, and pay attention to west. Okay, it changes its velocity uniformly to 10 meters per second. So that means 5 was your VI, 10 is your VF, but now it's going east. Okay, so we're going to choose one of them to be positive. It honestly doesn't matter which one you choose. I'm going to say west is negative, and I'm going to say east is positive. Okay, in 30 seconds, and that was your time. Okay, so just make sure you're paying attention to direction there, because when you're doing your math, positive and negative does matter. So we're looking for acceleration. We're looking for A. Okay, so I have V's, I have T's, I'm looking for A, so all this is a Daffy T problem. Okay, so my VI is going to be 5. Well, in this case, it's going to be negative 5. VF is going to be 10. Okay, time is going to be 30. A is going to be, we don't know, question mark. That means distance did not matter. Okay, so draw a line through that. So you're going to use equation number 1, so the whole VF equals VI plus AT. Okay, so we're going to do our VF, 10 equals negative 5 plus A, which we don't know, times 30. Okay, bring that 5 over, it becomes positive, which makes it a 15. 15 divided by 30, and you get acceleration of 0.5 meters per second squared. Now you can leave it as just positive since we decided that east is positive. Okay, positive is telling me that it's going east. You can still write east if you want to, okay, but that positive is going to tell me you're going east anyway. Part B is what is the displacement of the block in 30 seconds. We're doing the same thing, but now we're just going to flip-flop. So Daffy T again. T is still 30. VI is negative 5. Okay, didn't work there. VF is going to be 10. Okay, now we're looking for net displacement, so we're looking for distance. So that means we didn't care about acceleration, so we're going to use equation number 2, which is the D equals VI plus VF over 2, all times T. Okay, so we're going to plug in. So negative 5 plus 10 all over 2 times our time, which is 30. And we should get a displacement of 75 meters, and that is going east. Number 13, a body moving to 6 meters per second to the right, so pay attention to that. Okay, is acted upon by a force of 18 newtons to the left. Okay, so pay attention to your directions there. There's force. Okay, here's my velocity. After 12 seconds, so I gave you time, the body is moving in the same direction as the force at 6 meters per second. Okay, so this is my VF. Okay, so this is where we got to kind of watch out for is I'm going to say my right is positive and left is negative. So that means this force is technically actually a negative 18 newtons. And now my velocity is going the same as the force. So that means my final velocity is going to be negative 6. And then what is the mass of the body? So you're looking for your mass. Okay, so what we're going to do is we're looking for mass. The only thing that has mass is F net equals MA. Okay, well, I have forces. I don't have acceleration, though, so I can't do it. So I'm going to do is I'm going to set up Daffy T, see if I can find it. Okay, so my original velocity was 6. My final velocity was -6. Okay, and then A, what's what we're looking for? Time is going to be 12 seconds. That means we did not care about distance. So we're going to use equation number 1. So VF equals VI plus AT. So -6 equals 6 plus A times 12. Okay, so bring that 6 over, it becomes negative. Divide both sides by 12, and you get acceleration of -1 meters per second squared. Now I can bring that over to F net equals ma. So -18 equals my mass times -1. Okay, and divide both sides, or not, just divide by the negative, and that gives you a mass of 18 kilograms. Number 14, if mass 2 is 4 times as great as mass 1 and they are acted upon by the same force, so key thing there is same force is acting on them, what is the ratio of acceleration of mass 1 to that of mass 2? That can be kind of confusing to read. What we want to just figure out is mass 1 and mass 2. We know mass 2 is 4 times as big as mass 1. Okay, and they're both acted on by the same force. We want to know what does the acceleration look like for both of these. Okay, so remember we talked about the more mass you have, the slower it is for you to accelerate. So mass 2 is going to have, as far as acceleration-wise, we'll just say acceleration 2 is going to be 4 times slower than acceleration 1. Okay, because if it's the same force acting on both, mass 1 is lighter, so therefore it's going to make mass 1 move quicker. Okay, if mass 2 is 4 times as heavy, okay, that acceleration is going to be 4 times as slow. Okay, so that's all we were looking for there. Number 15, a mass of 1 times 10 to the -3 kilograms, so there's your mass, is acted upon by a force of 1 times 10 to the 2 newtons. Okay, so there's a force, and a time of 1 times 10 to the 3 seconds. Okay, so there's time there. What is the change in velocity? Okay, change in velocity is not asking for velocity. Change in velocity is asking for acceleration of the mass. Okay, so we're looking for A. Okay, we have F, we have force, we have mass. Therefore, time doesn't even really matter. Okay, so you don't, just because we give you stuff doesn't mean you have to always use it. Okay, you just need to figure out what you have and what you can solve. So F equals ma, so 1 times 10 to the 2 equals my mass, which is 1 times 10 to the -3, times my acceleration, divide both sides, and you get acceleration of 100,000 meters per second squared. Okay, which is probably not a realistic answer in this case, but this is just doing basic math stuff. Okay, you got to think about this is a very small mass, and that's a pretty large force. Okay, number 16, explain the difference between mass and weight. So mass is the matter that makes up an object. So no matter where you are, you have the exact same mass. Okay, if you're on Earth, if you're on the moon, you're in space, your mass is what makes up you. Weight is different though. Okay, weight is gravity affecting the mass. Not like changing your mass, but it's the effect that gravity has on your mass. That means your weight here on Earth is due to gravity. It's basically the force of gravity multiplied by your mass. If you go to the moon where gravity is lower, okay, you're going to have a lower weight. Your mass will be the same, but weight will be different. Number 17, compare the weight of a 200 kilogram object on Earth than on Venus. Okay, so we're going to take a look at, so this is our gravity for Venus. Okay, so we're going to do force equals mass times acceleration, so F equals mg in this case, because that's how you do weight. Mass would be 200. Now Earth would be 9.8. So multiply those and you get 1,960 newtons. That is the weight of that 200 kilogram object on Earth. So we're going to do the same thing for Venus. So we're going to take that 200 kilogram object, multiply by 8.5, and we're going to get 1,700 newtons. Okay, so now you see that your weight is different on Venus. Mass would still be the same, but weight would be different. What is the direction of both weights in the previous problem? Okay, so it is either down, okay, but say you're not perfectly down, say you're at the bottom of the Earth, okay, so that's not necessarily down, okay, or you could say it's towards the center of Earth or Venus. Okay, so that's basically what the attraction force is between an object, the center of one object, and the center of the other object. Okay, so number 19, 20, and 21, we did not do these. These are from last year. We took these out, so you don't have to worry about those. Number 22, state Newton's third law, the law of interactions. Okay, so that says for every action, there is an equal and opposite reaction. Okay, so that means if you push a wall with a certain force, that wall is going to push right back with the exact same force. Okay, so state the action and reaction forces to a tire hanging from a rope. Okay, so we have our rope here. Our tire hanging. So we have the force of gravity is pulling it down. So that would be considered our action force. And then the tension force on the top, okay, that would be considered our reaction. State the action and reaction forces of you pushing a shopping cart. Okay, so you're pushing a shopping cart. We'll just say you're pushing it to the right. So you have your applied force. That's your action. And then what's happening is a frictional force is going to be your reaction. Number 25, if a 75-kilogram boy pushes an 85-kilogram boy on a frictionless surface with a force of 550 newtons for 0.25 seconds, find the acceleration of each boy. Okay, so we have this mass, we have this mass, we have a force, and we have a time. So we're looking for the acceleration of each boy. Okay, so we're going to do the whole F equals ma. Okay, so our force is 550 newtons. Okay, so the force is being exerted on the 70-kilogram boy, and we're looking for the acceleration. So acceleration is going to be 7.86 meters per second squared. Okay, now we're going to look for the acceleration of the other boy, the 85-kilogram boy. Okay, so we're going to do 550 times 85 times A equals 85 times A. A is going to be 6.47 meters per second squared. Okay, so both of them are going to feel the exact same force, but it's your mass that's going to help determine who wins this. So say this was in a football game. Okay, so what these accelerations mean is when that 550 Newton force is exerted on the 70-kilogram boy, it's going to make them accelerate quicker. Okay, so that can be showing whether they lose the battle or not. Okay, versus the 85-kilogram boy. Okay, so that 70-kilogram boy is exerting the exact same 550 newtons back on the 85-kilogram boy, but since his mass is higher, his acceleration is going to be lower. Okay, so while it could slow him down, okay, ultimately the 70-kilogram boy is going to change speed quicker because it has a lower mass. Okay, so that's all that's stating there. And then how does a rocket accelerate in space where there's nothing to push on? Okay, I wouldn't get too worried about this one. This is just basically your action and reaction, so this is just more of the third law of practice. So what happens is the rocket pushes the exhaust out. Okay, so you have your combustion reaction is pushing that exhaust out. Okay, your reaction is going to be the exhaust gases that push back on the rocket. Okay, so that's basically how that happens in space is because there is no atmosphere. Okay, so how you propel through space is you're creating this exhaust, but at the same time the exhaust is pushing back on the rocket, and that's all you need to know for that one. And that'll end that video.